Hi, welcome. Today's video is on problem book page 906. We are going to be working on problem 8b together, and it's a heating and cooling curve problem. It's the fourth in the series for this unit, so if you haven't watched the other three, which are the specific heat video, the boiling point video, and the heating and cooling curve video, stop now, go back and watch those. Otherwise, this may be confusing. If you've already watched them, then I'm glad and you're in the right place. But get out your problem book. I'll pause the video and don't worry, I'll be right here when you come back. So thanks for getting your problem book so you can work it with me. So at the very top of the page on 906, it gives all this information about octane. And octane probably sounds familiar to you because it's a component in gasoline. And it gives us the three specific heat values, one for the solid, one for the liquid, one for the gas. We may use some of those. It also gives us the delta H of fusion, and the delta H of vaporization. So if we're melting or boiling, we might need one of those. It also gives us the temperatures of which the octane melts and which it boils at. So let's look at problem B. It says a 333 gram octane vapor is at 525 degrees Celsius, is condensed and cooled to 115 degrees Celsius, and they ask us at the top of the page to calculate the energy that is given off or required, and this time it would be given off, for this to happen. So how much energy is given off when octane cools from 525 to 115 if we have 333 grams? Also at the top of the page, it tells you what you need to do to solve these problems. It says first sketch a heating and cooling curve. So we're going to do that first. I've done the basics right here of the sketch. So you just generically draw this each time, and hopefully you've watched the videos and you know this first line that slopes upwards is a solid. The next sloping upward is a liquid. The next one is the gas. So you heat a solid and then you come to its melting point. It melts, and then when it's all melted, it heats up again, and it's a liquid. Then it reaches its boiling point. It boils until all of it's a gas, and then the gas is heated up. So this is a generic heating curve. We have to be specific for our material, which is octane. So we're going to heat it up until it reaches its melting point. So we need to know what that number is. So if you look at the top of the page, the melting point was minus 57 and the boiling point was 126. So whenever you do a heating or cooling curve, you need to label those. So I'm going to label the melting point, which is the first horizontal line, that's minus 57. And up here, the boiling point is 126. And these are in degrees Celsius. All right? So this would be the melting point, and this would be the boiling point, right? Now I have to figure out where I am starting on this graph. So I read the problem again, and I start at 525 degrees Celsius when it's a vapor. So I start way at the top here somewhere, so I'm going to label it right here, and I'm also going to write the number down on the side. So that's my starting point. Maybe I'll give the starting point a nice X so I remember that's where I'm starting. And let's draw that up. And let's see where we go down to. We condense it and we cool it, so I know it's changed into a liquid. And I'm at 115, and 115 is somewhere between the melting point and the boiling point, so I label it also. And here is where I end. So now, as the previous video said, anytime I change slopes here, if I go from horizontal to a diagonal line, every time I do that, I use a different step, or I use a different equation. So I'm starting up here. So step one is taking the gas and cooling it until it reaches its boiling point. Then it's going to condense. This condensing phase is a different equation. So that's going to be step two. And then cooling the liquid is going to be step three. So this problem, to solve this problem, I actually have to solve three problems. I have to condense the gas, I have to cool the gas, then condense it, then cool the liquid. So I'm going to use 3 different equations. So anytime I have a diagonal part of this graph, so here, here, or here, I use the Q equals MC delta T equation. And if it's a gas, I use the C for gas. If it's a liquid, I use the C for the liquid. If it's a solid, I use the C for the solid. So I go from here to here, step 1. Step 2, I do this horizontal line right here. That is when it's not changing temperature. It's just condensing. And I use Q equals M or N delta H. So which one am I going to need to use? Well, the delta H of vaporization is given to me in kilojoules per mole. So I'm going to have to use N delta H. And then I'm here, and I have to cool the liquid until it gets down there. So I have Q equals MC delta T again. So these problems are not long, and this was a gas, and now it's a liquid. They're just multiple steps. So if you're patient, you can solve them because the problems are pretty easy. This one just has 3 steps to a single problem. So now let's go and put the numbers into our equations. So step 1, we had Q equals MC delta T. The mass, as you're reading from problem book 906, was 333 grams. The specific heat of the octane as a gas was 1.66 joules per gram degree Celsius. And I'm not going to keep flipping back and forth all the time, so I'm hoping you're using 906 to see where I'm getting these values. And then I need the change in temperature, so I am going to flip for that. What was the change in temperature? Well, I started at 525, and then I don't go down to 115. That's a mistake people made, because this step only goes down to the boiling point, which is 126. So I'm going from 525, not to 115, but to 126. It'd be nice if we could do it in one step, but we can't because different things are happening. So I can only do this first part, 525 to 126. And that's a difference of 399 degrees Celsius. And you know I picked the right equation by the units. The grams cancel, the degrees Celsius cancel, and I'm going to get joules. So I take out my calculator and I plug 333 times 1.66 times 399. It's going to give me a pretty big number. What is that number? It's about 220,559 joules. That's a big number. So let's convert that to kilojoules, and let's also round to the correct number of sig figs. So we only need 3 sig figs, so I need to round here. So that gives me 221,000 joules, which also gives me 221 kilojoules. Okay, so step 1, that's how many kilojoules it takes just to go down from 525 down to 126, but I haven't condensed it, it's still all a gas. So now I have to condense the gas. So I'm using the Q equals N delta H of vaporization. So because it's condensing. So N, I don't have the N. I just have the gram. So I'm going to have to do a conversion because the delta H was in moles, so I'm still going to have to go to moles. I can't just leave it as grams. So I'm going to do this actually in the problem itself. You can do it separately, but I have 333 grams. I've got to convert that to moles, so I'm going to do this more like a unit analysis problem. So 333 grams, I look up the molar mass of C8H18, so that's 8 carbons and 18 hydrogens. And I get an answer of 114.23 grams of C3H8 for every 1 mole of C3H8. So you could solve that first and then plug it in the equation, but I'm going to kind of solve it together. So this gives me my N value times the heat of vaporization, which was 38.5 kilojoules per mole. And now once again, I'm going to check my units. Grams cancel, moles cancel, and this time I have kilojoules. And I plug it into my calculator and I round it and I get 112 kilojoules with 3 sig figs. And then step 3, back again to cooling, Q equals MC delta T, and this time it's a liquid. And so now I plug in the numbers 333 grams times the specific heat as the liquid is 2.23 joules per gram degree Celsius. And what's the change in temperature? So let's go back. I am going from 126 down to 115. So I'm doing this part of the graph. And that gives me 11 degrees Celsius. And I can only go to the ones place. So now I'm down to 2 sig figs. So I take out my calculator. So this was the mass given. This was just off the chart at the top of the page. And this is a subtraction. So multiplied together, I get 8.2 and round kilojoules. Now I'm not done because this is how much energy it took to do phase 1, part 2, part 3, and now I have to add them together. And remember, when we add things together, we don't count sig figs, we look at the place. So this went to the ones place, this went to the ones place, this goes to the tenths place. And the other thing I have to make sure is that I'm in the same units. Kilojoules plus kilojoules plus kilojoules. If one of these was joules and the rest was kilojoules, or 2 of them were joules and 1 was kilojoules, you would have to convert something to make sure they were all the same. So the last thing I do is take the 221 kilojoules plus the 112 kilojoules plus the 8.2 kilojoules, and I get a final answer of 341 kilojoules of energy is released. And if you want to put a sign on that, if it's being released, that means it's coming out of the system. That means it's exothermic. That means it could have a negative sign. So you can say either 341 kilojoules are released, or you can just say negative 341 kilojoules, because the negative replaces the word release. That tells me it's coming out of the system. So there you have it. So not too hard. It just takes a little time. So be patient with yourself and you can get these correct. So let's review the steps and write down these steps. 1, draw a heating cooling curve. So that's this generic up, horizontal, up graph. Label the melting point, the boiling point, the starting temperature, and the final temperature, so you know where you're going. What did we do step 3? We counted how many steps. We're going to need. Each change in this is a step. So the most you could have is 5. You could go solid, melt, liquid, boil, gas. 1, 2, 3, 4, 5 steps. But a lot of times you might just be doing 2 or 3 steps, and sometimes just 1 step. If you were just going from here to here, you would just be doing Q equals MC delta T, because you're all a liquid, you're not boiling or freezing or anything. So count the steps you need. Choose the right equations, which we had a video on that. So for each step, anytime it's diagonal, it's Q equals MC delta T. Otherwise, it's Q equals M or N delta H. 5th step, plug in, solve. Don't forget units, which will help you make sure you've chosen right, and sig figs. And there you have it. Not really difficult problems, just a little bit longer because they're multiple steps. Hope you followed that, and if you have questions, you can ask me when I see you next. Thanks for listening.